In this video, we will cover everything related to electromagnetic effects. So the title of the video and chapter is Electromagnetic Effects. And by electromagnetic effects, we mean that we will primarily study how magnetic fields interact with charges, such as free charges that come from the sun. For example, those are protons and helium nuclei usually, and as they travel from the sun to the earth, they interact with the magnetic field of the earth and they circle the planet. Then magnets also interact with currents, and a current in a wire is also moving charges, right? And magnets also interact with other magnets. So let's start with the definition of what a magnet is. So magnets are made of materials that have the property of exerting forces on moving charges, currents, and other magnets. So magnets always have a north and a south pole. This is almost everyday experience. I'm pretty sure that all of you have played with magnets at some point or another. So magnets always have a north and a south pole. Unlike the electric charge case, though, we can never separate the north from the south pole and get an individual north pole or an individual south pole, just like we can get a positive or a negative charge. Instead, if we cut the magnet in two, so if we have a magnet, okay, and this is the north pole and this is the south pole, and let's assume that we cut it into two, what we will get is two new magnets that will have a north pole and a south pole each, okay? So we can never, and if we keep cutting it, we will keep getting new magnets with north and south poles. We'll never get an individual north or an individual south pole. In fact, the existence of magnetic monopoles is a mystery in physics that is not totally resolved for the past 100 or so years, but this is something out of scope for these lessons. Now, magnets create fields around them, okay? And that field is denoted by the capital letter B, and it's called magnetic flux density, okay? So the magnetic field is denoted by B, and I'm gonna put an arrow on top of the B because this is a vector field. Just like the electric field is a vector field, just like the gravitational field is a vector field. And what is a vector field? It's a field in which a mass will feel a force. In the case of the gravitational field, a charge will feel a force. In the case of the electric field and in the case of the magnetic field, another magnet is going to feel a force or currents or charges, okay? So magnetic field, the magnetic field is denoted by B. It is called magnetic flux density, and it is measured in units of Teslas. So capital T is the unit, the SI unit. And I know it's not related to the cars. It's actually related to Nikola Tesla, a Serbian physicist from also about, I think, more than 100 years ago. Okay, so let's design this field around a magnet. Okay, we have a north pole, say, and a south pole. I'm gonna use red. So magnetic field lines always start from north poles and end in south poles, okay? So this is what's going on. I'm sorry, okay. So something like this. So magnetic field lines form closed loops, okay? So let's write that down. Field lines go from north to south. Actually, let's write always go from left to south. From north to south. So let me cut this, make some space. So field lines, oops, I'm sorry about this. So field lines always go from north to south. They form closed loops. They never cross. And the stronger the field, the denser the lines. Okay, and let me show you how these lines interact with each other. So for example, if we apply this rule to two magnets, so let's say I have two magnets and I put the south poles across each other like this. So here's my south pole and this is my north pole. Then here, what's gonna happen is that, actually, let me erase this. So I'm gonna have south pole lines coming into the south pole, okay? And nothing special happens on this side, okay? Maybe they come like that, okay? But the concept here is that here at this point we have repulsion, okay? Because magnetic field lines do interact with each other if we have two magnets. And if we have south poles or north poles across each other, we get repulsion. Okay, now let's go see what happens if we have a north pole across a south pole. So if the situation is like this, now we have magnetic field lines exiting the north pole and entering the south pole. So in the field, in the space between the two magnets, we get a uniform field, actually, almost uniform field. And of course, attraction, okay? So opposites attract in the case of magnets as well. Now, let me draw a few more lines actually before we move on. So we also have lines that exit the North Pole and enter the South Pole like this. And the same for this magnet, okay? All right, now the key concept to keep from this discussion is that magnets have north and south poles. They have magnetic field lines. The magnetic field is called magnetic flux density and is measured in Teslas. Now let's go define another quantity of interest, which is the magnetic flux. So magnetic flux is the next thing we're going to talk about. It is denoted with the capital Greek letter phi. And by the way, I don't think I ever mentioned this in these videos, but I'm Greek, okay? I'm from Cyprus, so we speak Greek. So it's my native language. Anyway, so magnetic flux is the product of B and a cross-sectional area through which Actually, let's write it. And a cross-sectional area that B cuts through. What do we mean by that? Let me show you. So here is a cross-sectional area. It can be a disk, it can be a ring. It's usually something metallic when we deal with magnetism. So let's say that this is the cross-sectional area, A, measured in square meters. And let's say we have let's keep the red for the magnetic field. So let's say, that we have some magnetic field B. I'm gonna use the hat again because it's a vector, cutting through this cross-sectional area. Then the flux, the magnetic flux is given by B times the cross-sectional area. It has units of YB, which stands for Weber, and 1 Weber is 1 Tesla meters squared. And I haven't made a comment about the unit of Tesla yet. This is a huge unit. So what do I mean by that? The strongest magnets that we have on planet Earth have a strength of about 2 to 5, maybe 10 Teslas. And we are talking about MRI machines usually, or magnets that are used in science research. So they're used a lot in nuclear physics research and particle physics research. As far as I know, okay, I'm a little bit biased with nuclear physics, but I'm pretty sure it finds applications in other fields as well. Now, let's quickly define the concept of magnetic flux linkage. So magnetic flux linkage, which is simply n phi, okay? Which, why is it n phi? If we have n loops of cross-sectional area A, so if we have n loops of cross-sectional area A, then the total flux is n phi, which is equal to n BA. So we get one contribution from each loop. And let's draw that. So let's say we have one loop here and another loop here. Sorry for the bad drawing. Let's assume that the cross-sectional area is actually the same. I know it's not, but let's assume it is. So the flux linkage for this case is going to be 2BA, right? And if we have a coil, which is usually the case, most usually, it looks like this, okay? Let's assume that the cross-sectional area is A, and there is some magnetic field passing through it. Then in the second case, phi, sigma phi, the total flux linkage, is going to be N times B times A. And we assume that we have N loops, okay? Now, what happens if the magnetic field cuts through the cross-sectional area at an angle, okay? First, actually, let's go see the extreme case. Remember that in the definition, we said that magnetic flux is the product of B and the cross-sectional area A that B cuts through. So, okay, let's go see a silly example. This is my cross-sectional area A, and here is my magnetic field, okay? I'm trying to show that it's parallel to this cross-sectional area. Does it cut through? No, it does not. So phi is 0 in this case, okay? So we need the magnetic field to cut through the loop. So let's assume that now the magnetic field cuts through the cross-sectional area at an angle theta, okay? So if the field lines, okay, the magnetic field lines cut through the surface, at an angle theta, we need to resolve B into a component perpendicular to A, where A is the cross-sectional area. So what do I mean by that? This is my cross-sectional area, and let's say my magnetic field goes like that, and let's assume that theta is the angle between the cross-sectional area and the magnetic field. Then we can analyze the magnetic field into a component that is perpendicular to this cross-sectional area, and since theta is this angle, then this is B, sine theta. And we can, of course, analyze this magnetic field into horizontal component as well, which is going to be B cosine theta. But B cosine theta is parallel to the cross-sectional area, so the contribution to phi is 0. So in this case, phi is B sine theta times A. What happens if they give us the other angle? So let's say that I have the same cross-sectional area A, and instead of giving us the angle with respect to the horizontal, they give us the angle with respect to the vertical. Let's call this phi. Okay, again, we resolve. So this is B, by the way, and this is B. So again, we resolve the magnetic field into the component that is perpendicular to the cross-sectional area. This time is B cosine phi. So in this case, phi, the magnetic flux, is B, cosine phi times A. Okay, so anything that goes parallel to the cross-sectional area gives 0 contribution to the magnetic flux. Okay, now let's talk about magnetic forces, and specifically the forces magnets exert on current carrying wires. Okay, so sorry, that was a mouthful. So magnetic forces. So magnets exert forces on current carrying wires. Okay, so let's assume, let me try to draw. This is going to be a little bit hard. So let's say that, okay, here, okay, so this is the north pole of a magnet, and to create a uniform magnetic field across this magnet, I have, okay, over here, okay, and you can imagine it like that, and I have the south pole here. So between these two magnets, I set up a uniform magnetic field B. Okay, so this is my B. Now assume that perpendicular to this B, there is a current. Okay, there is a wire that carries some current I. Okay, and this is the current I. So assume that this closes to infinity, and there is some battery that creates this current. Okay, so this is my battery. Okay, sorry, these are not connected. So let's say I have a battery pack that creates this current. Now, in this example I'm showing here, the current I is perpendicular, right, to the magnetic field lines. Therefore, according to Fleming's left-hand rule, this force is upwards. Okay, so I used all colors here. Let me choose a different color for the force. Let's use orange. So the force F is perpendicular to the magnetic field lines. I know this is a little bit complicated because this is a 3D scenario, okay? but the force is going to be upwards. Okay, so once we put a current into a magnetic field, that current is going to experience a force. Okay, and the direction of the force is given by this guy Fleming. So Fleming's left-hand rule that tells us what? How does this work? First of all, we have to use our left hand. Okay, I know it gets confusing sometimes because people might try to use their right hand. It doesn't work. You have to use your left hand. Okay, so if your index finger is B, so you put your fingers along the direction. So you put your index finger in the direction of B. So this direction, okay, that I'm showing there with the little arrow. Okay, and then you put your middle finger in the direction of I. So this is the direction of I, okay? And then your thumb is gonna point in the direction of the force. So immediately you see that, where is the orange I was using earlier? Here is the orange. So this is my B, this is my I, so this is my F, perpendicular to these two, pretty much, okay? So index is B, middle finger is I, and thumb with a B will give you force, the direction of the force, okay? Now, actually, let me make this a B. So you always start with the left hand, you put your index finger in the direction of B, your middle finger in the direction of I, and the last one is your thumb, and it's gonna point towards the direction of the force, okay? There is a caveat here. Note, if I, the current, is parallel to the direction of B, F is automatically 0, okay? So I draw this. Let me quickly draw this actually. So what I mean by that is, so if that's, okay, I'm gonna draw it quickly. So this is my North Pole, this is my South Pole. Okay, this is my South, this is my B, same as before. And let's say that I put a current in the same direction as I. So maybe I have a battery like this. Okay, so I is in the same direction as B. Then in this case, the force is 0. Okay. And again, when the current makes an angle with the magnetic field, we will have to resolve that current into a horizontal and a vertical component like we did with the magnetic flux. I'm going to show you in a while. Okay. But for now, keep this in mind, that if the current is parallel to the magnetic field, we get no force. So a cool little thing we can do is to create a motor, okay? So what do you mean by that? This is going to be really hard to draw. So let's title this magnetic motor or rotor, as it is called. So I'm going to draw again my north. Actually, this is huge. So this is the North Pole, and this is the South Pole. Okay, and this is the magnetic field in between. So I'm going to use the green color to create this rotor. So let's assume that I have a square like that, okay, in which current is flowing, okay? So this is the direction of the current. Now, for this section over here and this section over there, there is no force, okay? But in this direction, so on this side, so this side, this wire that carries some current is going to experience a force that points upwards. So we have a force upwards in this direction, and in this direction in which the current is flowing upwards. So again, we can use Fleming's rule. So we have B in this direction, we get I that points up, right? So I points in this direction, so the force is gonna point down. I'm sorry, this might be confusing, but the idea is that we have a pair of forces which create a torque, right? So if we put a square like that, a square wire in the space between two magnets that set up a uniform magnetic field, that wire is gonna spin, okay? So we have a pair of forces, and this is because the current points in opposite directions, in the opposite sides of this rectangle, and therefore we have a pair of forces which creates a torque which makes the rotor spin. Okay, so it's in your book. I think it's a nice little thing to know. Okay, and remember the sides, so this side of the square, so this side and this side feel no force because the current and the magnetic field are parallel to each other. Okay, now let's do some math. Let's define this force. Let's quantify this force. Okay, so let's do the math. The force on the wire is given by F BIL. This is how it's known, F B. So force is equal to the magnetic flux density times the current times the length. Okay, and remember that we have 1 Newton on the left hand side because it's a force, and on the right hand side we have Teslas times amperes times meters. Okay, so 1 Newton is equal to 1 Tesla times 1 ampere times 1 meter in base units. Okay, now let's go see the special case of a current at an angle that I mentioned but didn't explain further earlier. So current at an angle. So again, this is getting tedious. In future videos, I might think of better ways to do this. Guys, if you have any suggestions, let me know, because as I mentioned in other videos, this is the first time I'm doing this. So in a classroom, it's easier because you can draw these ones and then keep using it again and again, but it's not easy on my iPad. So if you have better ideas, let me know. So here are the magnetic field lines B. And let's say that my current makes an angle. So maybe this is the situation. Okay, this is I, and it makes an angle theta with respect to, okay, let me bring I on this side. Let me erase this because I will need some space there. So again, what do? We analyze this current I into a component that is perpendicular to this magnetic field line. So this is going to be I sine theta, right? And of course, there is a component I cosine theta that is parallel to the magnetic field lines. Anything parallel to the magnetic field lines, though, gives zero contribution to the force. So we only need this component, and we plug this component in the F BIL equation. So F is going to be B times L times the current that is perpendicular to the magnetic field lines, which is I sine theta. Okay, and you can see from this formula that if theta is 90 degrees, we get F equal to BIL, right? And if theta is 0, F is 0, just like I told you. And the same goes for 180, of course. Okay, if theta is 180 degrees, again, we get 0. Okay, so the math worked out. Now, let's go talk on the force on charged particles that move with some velocity v. Okay, magnetic fields do not exert forces on static charges, that is, charges that do not move. They only exert forces on moving charges. Okay, so particles that carry charge and they have some velocity v. What kind of particles? Usually protons, helium-4 nuclei, helium-3 nuclei, even sodium nuclei. Any kind of nucleus that is stripped of its electrons will be accelerated, not accelerated, move, feel some force from the magnetic field. So we'll see magnetic fields do not accelerate particles. So what I said was wrong. Okay, they only change the direction of motion of particles, as we will see. What does that mean? That an acceleration is generated, okay? But it's gonna be angular acceleration, okay? In terms of speed, magnetic fields cannot speed particles up, okay? Only electric fields can speed particles up. So, but we will talk about that further when we get to it. So, next concept, force on charged particles moving with velocity v. So I'm just gonna give you the equation and I'm gonna attempt something like a proof. It's not complete proof, but it helps to understand what's going on qualitatively. So QVB is the force, okay? Now let's go check something. So let's call this loose proof. So it's kind of like, maybe loose is not a good word. It's not a good word. Let's use informal proof. Okay, so let's assume, actually no, let's start with F BIL, B-I-L. Okay. Now, what is current? Current is simply Q over time, right? Times L, because charge over time represents current. Okay. Now let's keep our Q because we need it. Q times B, and then we have L over T. So L over T is the velocity of one particle, say inside a wire, okay? So this is just V. So we get Q, V, B, okay? But this only applies to an individual particle inside a current. So you can imagine charges inside the current. So if we isolate one of these charges, then we will see that the force on this individual charge is QVB, where V is the velocity of this charge. Now imagine that we remove the wire completely and we just have free charges, okay? So now the charges are free to move and they have a velocity V. Then the force they're gonna feel is QVB, okay? And then the same thing applies if the particle makes an angle theta with respect to the magnetic field lines. So I'm not going to draw the scheme again because it's getting tedious. If the particle makes an angle theta with the magnetic field lines, actually let's write with WRT means with respect to the magnetic field lines, comma, then the force felt by the particle is F equal to QVB. So this is what we mean. So this is the situation. As the particle moves with some velocity v, say, it makes an angle theta with respect to the magnetic field lines, okay? In that case, the force is going to be QVB times, in this case, we need the component perpendicular to this current, so it's going to be QVB sine theta. Okay? And again, if theta is 0, meaning that the particle travels in the same direction as the magnetic field lines, then the force is 0. And if theta is 90 degrees, the force is QVB. Now, how about the direction of this force on moving particles? So, direction. If the charge is positive, then we apply Fleming's left hand rule, like we do with currents. But if the charge is negative, we again use Fleming's left hand rule, but flip our thumb. Now let's go see the consequences that this force exerted on a moving charged particle has on the particle's motion. So, effects of QVB on a particle. And this, guys, is going to be useful when we study particle detectors and such. But for now, let's first define two symbols. So if I do this and I refer to a magnetic field, I'm referring to a magnetic field that points into the page. And this is because imagine an arrow in space, like, or maybe you're throwing darts. So when you see the arrow heading away from you, you only see the X of the arrow, right? So this is why it's the X when it points into the page. And if it points out of the page, B, if I draw this, B points out of the way, and this is because if an arrow is headed towards me, hopefully not, but if it's heading towards me, I'm gonna see the tip of the arrow, so I'm gonna see a dot, okay? So let's imagine that we have a region in space where B is pointing inwards, okay? So this is my B. And these X's here further demonstrate or show that the magnetic field in this rectangle that I drew points into the page, okay? Let's assume that I have a positively charged particle with charge plus Q traveling with velocity V up, okay? Now and it enters this region, okay, where there is a magnetic field, B. So my left hand rule, Fleming's left hand rule says that B points into the page. So I put my index finger in the direction of B. Then V, I have to make my middle finger point in the direction of V. And then my thumb points to the left, okay? So the force is gonna be a force to the left. And notice that the force is perpendicular to the velocity, okay? So what is this force going to do? It's gonna start bending the particle outwards, okay? And again, the velocity here is gonna be V, and F is gonna be perpendicular to the velocity. Now, let us go see what's gonna happen to a negatively charged particle, minus Q, traveling with velocity V into this space where the magnetic field is into the page. So let's use Fleming's left hand rule for the negatively charged particle. So we put our index finger into the page. We put our middle finger in the direction of V, and now our thumb again points to the left. But because it's negatively charged, we have to flip our thumb. So our thumb points to the right, okay? So this is the direction of the force, which is again perpendicular to this velocity. So at a later stage, the particle is gonna bend inwards, and it's gonna pretty much, as we will see in a moment, this means that since the force is perpendicular to the velocity, then we have a centripetal force, right? And this centripetal force is gonna make the particle undergo a circular motion, okay? But before we see that, let's, for completeness, let's do the case of B pointing out of the page. Okay, the way I drew it like that, it makes it look like eyes. Okay, so no, it's not eyes, I'm sorry. So yeah, that's my B. Okay, now if I have a particle traveling with velocity v up in the direction up in the page, and B points outwards, so I have to put my index finger pointing up, and then now V points V points out of up into the page, so the force is to the left. Sorry, got confused. I confused myself. So F bends the particle inwards. Okay. Now for the negatively charged particle, we put our index finger pointing out of the page. We put again, it's gonna be the same situation, but with our thumb flipping this time. Okay. So the force is gonna be inwards. Okay. So these two particles will bend towards each other. Okay. So let's go do the math. So in both cases, F is perpendicular to V and F is perpendicular to V here as well. So since F is perpendicular to V, F is a centripetal force. Okay, and remember that Newton's second law tells us that F is ma, but A is V squared over R for circular motion. So we have F equal to ma, so QVB is mv squared over R. And here there are many things we can do. We can cancel V first of all. So immediately we find that Q over M is V over BR. Okay. This is a significant result in physics because this was one of the first quantities that were calculated when people were studying electrons. So first they figured out the Q over M, charge over mass for the electron, and then they found the charge and mass individually. Okay. So at this point, I'm gonna write a very important result that you have to keep in your minds at all times, that magnetic fields never accelerate particles in the sense of increasing their speed, because they do accelerate the particles, but they accelerate them in the sense of changing their direction. So magnetic fields bend particles, they don't accelerate them, they don't make them speed up. Okay, so magnetic fields never accelerate particles in the sense of increasing or decreasing their speed. They only bend particles. Okay, electric fields do accelerate particles. Okay, so using electric fields, we can increase the speed of a moving particle. Okay, now this next topic I'm going to discuss is claimed to be not part of your syllabus, but it's in the book, and I'm going to cover it anyway, just for the sake of it, and also it's better safe than sorry. So sometimes in the A-levels they ask difficult questions that are on the fringes of what you're supposed to know. So let's write this down, extra. Okay, so extra, and I'm gonna title this as combining E, an electric field, and B, a magnetic field. Okay, so assume that you have some setup here that has some potential difference V, so some voltage, okay, voltage V, okay, and you have some particle that starts from rest on in this setup, okay, and let's assume that there is a hole in this setup that allows the particle to exit. So it starts with velocity V here on the left plate of some sort of a capacitor, and once it makes it to the right plate, it finds a hole that helps it pass through with some velocity V. Please don't confuse this V with the voltage. I'm gonna write the voltage with red color, okay, to avoid confusion. Okay, and let's assume that it travels in vacuum. It needs to be a vacuum because charged particles stop within a few centimeters, maybe meters of air. So this thing has to be in vacuum, okay? And now let's assume that there is a magnet here, okay? So there is some magnet, okay? Magnet. And between these magnets, there is some magnetic field. So what's gonna happen? Maybe the particle is gonna feel a force F downwards, into the down in the page and bend, okay? So this is what people do when they study nuclear reactions or particle reactions. They use combinations of electric fields to increase the speed, to increase the kinetic energy of particles, and magnets to bend them so that the particles are heading towards a direction that someone needs them to be, okay? Now, if we apply the principle of conservation of energy in this setup, we get the following. Q, the charge of the particle, times the voltage, which I write in red. So first, let us find this velocity V. Okay, the velocity does not change when the particle enters the magnetic field. Only the direction changes, remember? So Q times the voltage should be equal to the kinetic energy, which is 1/2 mv squared, right? 1/2 mv squared. And if we solve for the velocity, we find that the velocity of the particle, once it exits this setup there, should be 2q times the voltage, which is in red, over its mass, okay? So if we go back to this equation and name this equation 1, oops, what happened? So I'm sorry for that. So if we name this equation 1 and this equation 2, okay, we find that from 1 and 2, we get, and by the way, equation 2 applies when the particle enters this magnet, okay? So from equations 1 and 2, we get that Q over M is V over B times R, but V was calculated. So first of all, let's square this. So Q squared over M squared is V squared over B squared times R squared. So let me use a clean page. So Q squared over M squared is V squared, which is 2Q times the voltage. I'm gonna use red for the voltage, okay? Over B squared R squared, okay? We get some cancellations. Did I mess up something? Ah, yes, and we have the mass in the denominator. So Q and Q cancels, M and M cancels, and we get that Q over M is in fact equal to 2 times the voltage, the applied voltage that we have control over, at least in an experiment, okay, over B squared times R squared. What does this equation tell us? This equation tells us that particles that have different charge or different mass will undergo circular motion that has a different radius, okay? So this method helps you distinguish particles between them. So I'm going to write this down. So different particles And what do you mean by different? Having different Q and or M will undergo circular motion with different radius. The next topic is generating electricity. So let's go back and recall a concept that we started this video with. So recall that phi is B times A, or phi is N times B times A whenever we deal with coils or multiple loops, okay? So recall that phi is the magnetic flux, right? And again, it's measured in Webers, which is Teslas over meters squared, okay? So this is the situation. We have a cross-sectional area and B, and phi is B times A. Now, let us recall one more result from physics that we haven't mentioned yet. You probably know it from earlier physics lessons. So also recall that moving charges or currents create magnetic fields. And I'm gonna discuss two situations here. So let's assume that we have a wire and a current moving up in this wire. Then this current creates a magnetic field that if we put our thumb of our right hand now in the direction of I, then B curls around our fingers, okay? And if the current is going downwards, then again we have to put our thumb in the direction of the current, and then our fingers curl in the direction of the magnetic field, which is now in the opposite direction, okay? Or is it the same direction? Sorry, this is a mistake. So B points in the opposite direction, okay? The other example I'm gonna draw is that of a coil. So let's assume that we have a coil and there is a current in this coil that goes in this direction. So now we curl our fingers in the direction of I, and B is in the direction where our thumb points, okay? So B goes up in this coil, and if we have a coil that goes this way and the current goes down, if we curl our fingers in the direction of I, then our thumb points in the direction of B, therefore B is downwards, okay? Now, why am I saying all these things? Because according to Faraday's law, when the magnetic flux through a surface changes with respect to time, an EMF, and EMF stands for electromotive force, is induced. Okay, so the electromotive force is denoted with the capital Greek letter epsilon, and it's equal to minus delta phi over delta t, or E. Actually, let me bring it here. or E is minus delta n phi over delta t for a coil with n turns. So now what is mth? Mth is voltage. So we are kind of like get a battery of some sort, okay? Mth is measured in units of voltage. Now let's go see one more thing. Also, since phi is B times A, then if for a moment we switch away from delta phi and we use d phi over dt, which is the instantaneous change in flux with respect to time, then E is minus d phi over dt, which is equal to minus d b times a over dt. And now from the derivative rules we get two terms, minus dB over dt times a minus b dA over dt. So whenever either the surface area or B change with respect to time, we get an mth. Okay, let's go see a few examples. So examples. So let's say that I have a coil, okay, sitting somewhere in space. Nothing is happening to it. It's not moving. Nothing is going on. And we have a magnet that moves with velocity v in and out of this coil. Therefore, if these are the magnetic field lines, we see that if we bring the magnet closer to the coil, the flux increases because the amount of magnetic field lines that cut through the coil increase. So in this case, changing B creates an mth in the coil. Okay, since the cross-sectional area A, if this is A, the cross-sectional area of the coil does not change in this case, right? Another example is the example of, say, I have a region in space with some magnetic field that points into the page, and then I have a ring, okay, that travels with velocity v and enters this magnetic field. So in this case, the magnetic field is constant. It's equal to B. It doesn't change with respect to time. But the moment when this guy, let's use blue, the moment that this ring enters this region, this region, okay, the moment it enters here, its surface area that is exposed to the magnetic field changes. So the moment it enters, it gets a change in magnetic flux, therefore a current is induced on that loop. But once it is in the magnetic field, the area does not change, so that current goes to zero. But the moment it exits, the area, and it keeps moving with velocity v, obviously, and the moment it exits, the area again changes, so we get a current when it exits. So I'm going to write this down. In this case, we have changing cross-sectional area A, and B is constant. So in this case, we also get a magnetic, an EMF. Now, the last example I'm going to show, and then I'm going to show a cool simulation again. So let's say that I have my silly magnets like before, north and south, okay. Sorry for the bad drawing. So these are the magnetic field lines. And let's say that I have a ring like that, that spins in this direction, okay? So it spins in a direction that makes this ring at points. There are points in its motion in which it's parallel to the magnetic field lines, and there are moments in which it cuts through the magnetic field lines. So in the rotating coil example, we constantly change the surface area exposed to the magnetic field lines. So again, we have changing A due to rotation. Therefore, we get an EMF. And I deliberately did not talk about this negative sign. There is a negative sign coming with this definition, but I'm gonna address that later. For now, let's go see a cool simulation. Okay, guys, so you see how if I move this magnet in the vicinity of this coil, I change the magnetic flux through the coil. So when I move in, I increase the magnetic flux, and when I move out, I decrease it, etc. But in any case, I generate electricity, okay? So if there is a closed loop, and what do you mean by closed? Such that a current can flow in the loop, then E, this EMF, will generate a current in the circuit given by I equal to E over R, where R is the resistance of the circuit, okay? And the second thing we haven't covered yet is Lenz's law. Which is related to the minus sign of the equation I showed you earlier. Lenz's law tells us that the direction of the induced current is such that it opposes the change that creates it, the change that created it. So let me show you an example. Let's say that I have a circuit with a resistor R, an ammeter, and let me try to make a very simple coil. Okay, and let's say, actually, let me bring this down. Okay, there. Oops. Let me, okay, here. And let's say that I have a bar magnet with its north pole and its south pole falling into this coil. Then when it approaches the coil, okay, a current will be generated in a direction that points in like that. And the reason is that, remember that if we curl our fingers in the direction of current, then our thumb points towards the direction of the induced magnetic field. So the north pole, so B is gonna be like that, therefore the north pole, by the way, the arrow in the direction of B points towards the direction of the north pole, okay? So a north pole will be generated here to oppose this north pole of the magnet, and a south pole will be generated there. So the moment this magnet tries to enter this coil, we're gonna have a current generated in this direction. And then let's take this situation a moment later when the magnet went through the coil and it's now falling out of the coil. So circuit is the same. R, we need an ammeter, and we need a coil. Okay, it's a very simple coil. Actually, again, I will have problem with space, so let me do this. And this is my magnet now. Oops. Okay, when it exits the coil. So the North Pole is still there and the South Pole is still there. Now a current will be generated in this direction. Okay, so it's gonna be in the opposite direction, in the reverse direction than before. And again, if we curl our fingers in the direction of I, we will find what the direction of the North Pole would be. So the North Pole generated due to this current is gonna point, it's gonna be here now because it wants to attract back this magnet. But in the previous scenario, the coil repulses the magnet. Okay, so as I said, I am Greek, so I come from the sea. So it's a similar situation as when you take your first bath in the sea. You don't really want to get into the water sometimes because it's cold, but if you get into the water, you don't want to get out. So it's the same here. The magnet initially does not want to get into this coil, but once it gets into the coil, it doesn't want to exit. Finally, we made it to the end where we will talk about transformers, not the cool ones from the movie, the ones used to reduce the current that comes from the power plant, the voltage from the power plant to the voltage needed in houses, and self-induction. Okay. Now let us start with this setup. Okay. I'll try to have space to draw what I need to draw. So this is an iron core. So it's a piece of iron pretty much, on which we wrap a coil like that. With let's say NP, where P stands for primary, with NP number of turns, and we apply some voltage here. Let's call it VP, primary voltage. Okay, and there is a switch. Okay, so something like that, and there is a switch S to switch that voltage on and off. And on the other side of the coil, we wrap another. On the other side of the core, I'm sorry, we wrap another coil with NS number of turns, which means secondary number of turns. And we have a voltmeter to measure the voltage VS that exits this coil. So what's going on here? Once we close this switch, there will be a current in this coil, which is going to generate a magnetic field B. Okay, let's assume that B is going to be in this direction. Due to the iron core, this B is going to travel through the secondary coil, okay? And because it travels through the secondary coil, it's going to induce some voltage in the secondary coil, okay? So this is what we mean by self-induction, that we get the generation of electricity due to electricity changing in one side of this iron core. So I'm going to write this down. If S is closed, current flows through P, the primary coil. This induces a magnetic field due to this current. B travels through core to secondary coil. Let's call it S. Okay, to S. There is a change in magnetic flux in S, therefore an EMF is generated in S. Can we find how much EMF is induced? Yes, because EP in the primary coil, the induced current, the induced EMF in the primary coil is equal to VP pretty much, okay, which is equal to minus the number of turns NP times delta V over delta T. Then the EMF in the secondary coil is going to be the number of turns of the secondary coil times the same change in flux with respect to time, because the same beat travels between both primary and secondary coils, okay? So from here we see that pretty much EP over NP is equal to ES over NS. Therefore, V P, which is the voltage in the primary coil over the voltage in the secondary coil, is equal to the number of turns of the primary coil over the number of turns of the secondary coil. So this setup is used to drop voltage. So an application can be drop voltage for house applications.